Section 15.1, refraction. We're going to take a look at recognizing when refraction actually occurs. We're going to identify the direction the light will bend as it passes from one medium to another, so how the angle changes. And then we're going to use Snell's law to determine the actual angle or the index of refraction that's needed to determine what the unknown material may be. So first, refraction is the bending of a wave as it passes at an angle from one medium to another. So note right away this has to be at some sort of an angle here. If the light wave came in perpendicular to the glass surface like this, it would go straight through. But because it comes at an angle, the light waves are going to get bent. Now theta I is used to denote what's called the angle of incidence. And theta I is measured from the normal always. So you're going to always see a dash normal here. And this is going to be your angle theta incident. So this might be like, say, 45 degrees here. And notice that the refracted angle, the angle from the normal, which should be equal, is not. Again, if these were vertical angles and these were straight lines, these would be equal. This ray would continue in this direction. But we're seeing that it doesn't continue in this direction. It's shifted inward. So this theta R value is less than theta I. Now, the reason refraction actually occurs is because the light waves, they travel at different speeds throughout the different media. So, and these media have to be transparent, obviously, or else it wouldn't pass through. But going from air to glass, think about what's happening there. It's a different interaction with the molecules, so it slows down the wave fronts. And when this happens, it could result in the wave slowing down or the wave speeding up. If the light moves from a material where the speed is higher to a material where the speed is lower, so for example, think about light and air. Well, light and air is going to travel as fast as it possibly can. Air is close to a vacuum. So the speed of light in air is going to always be greater than some other material. So here it's going from a high speed material with a large angle, and suddenly it's in a lower speed material, it bends toward the normal. So again, when it goes from a faster to a slower moving material, it's going to bend toward the normal. And thus theta R here is going to be less than this theta I value. And the opposite is also true. We'll see that here. Right? It starts with a small angle and it bends away from the normal. Look how much bigger this angle is. It should finish this way, right? If we continue this as a straight ray, it should go like that. But it clearly is all the way out here, so it bends away from the normal. So from slow to fast, it bends away from the normal. So again, the opposite is true. So we're going to define something called the index of refraction, which is going to be kind of like a material property that we've talked about before. So we've talked about things like density, and you should have heard of density before. We've looked at material properties of different materials like the coefficients of friction between wood and a surface like Teflon or glass and metal or ice. They have different indices where their coefficients of friction are different. So this index now is going to be just another number that represents a material property. And what it is, it's a ratio that compares the speed of light in a vacuum to the speed of light in a given medium. So for example, if you wanted to find what the N index of refraction value is for something like glass, you would take the speed of light in a vacuum, that's this right here, and compare it to the speed of light in that medium. So whatever the velocity of light is in glass. And what you'll notice is, if you remember about the speed of light in a vacuum is the greatest possible velocity. So this number up here has to always be bigger than this number. So just pick two numbers, make the top bigger. It doesn't matter what they are. So like 7 over 4. That's going to be some number bigger than 1. Or a number like 6 over 5. That's got to be bigger than 1 as well. So whenever the numerator is bigger than the denominator, you always have a number that's greater than 1. So this index of refraction will always be bigger than 1, except when we're in air. Because we'll say that air, the velocity is so close to the speed of light in a vacuum, right? In air, we'll say that these two numbers are pretty much the same. And we'll see that in the next table in a moment. Notice as well that these are going to be unitless numbers, because this unit is meters per second and this unit is meters per second. So n, like mu, the coefficient of friction, has no units. It is dimensionless. And here we'll take a look at a table of indices of refraction for various substances. So for example, here we'll see cubic zirconia, diamond, fluorite, fused quartz, different types of glass, ice. Now we're going to look on the other side. We're going to see we have liquids and gases as well, and these are going to be at different temperatures. So we're looking at the different temperatures here for each of these, and this is standard temperature and pressure here for gases. And what we'll notice is that in air, the speed, or the value that you get for n when using the speed of light in air is so close to 1 that we really just assume that the n value for air is going to be 1. So when we say that something comes from air to another material, well, air is going to have a value of 1 for its n value, so the other n values are always going to be larger than 1. And we'll see that diamond and cubic zirconia, two materials that we know have a tendency to do something called sparkle, and we'll talk about that reasoning for the sparkling, has to do with this n value, the index of refraction, how it can bend light. That's what causes that sparkling. So there's a phenomenon that occurs for certain materials more frequently than other materials. And we'll see that phenomenon in the next section. So one other thing that we can say is that the greater the index of refraction, that n value of the medium, the more refraction occurs, which means the more the light is bent toward the normal. That's what refraction is, the bending of light toward the normal there. So the higher the value on the other side. So another way of saying this is that the higher the value of n of the medium, the lower the value of theta r is going to be, because it's going to bend really toward that normal. It's going to be a small theta r value. Let's take a look at Snell's law now. Snell's law tells us the following relationship, that the index of refraction of the incident material, so the first material that it's passing through, so if we were drawing a diagram here, the light's coming from this material, it hits the normal, and then maybe bends really far away from the normal. It doesn't pass through on the path you would predict it to pass through on, right? This path, it's not what it comes through on. So this ends up being theta I, the incident material. So this material is Ni. So if this was air, Ni would equal 1, if it were air, for example. Then on the other side we have Nr, so this is the whatever the second material is, and this is theta r right here. So example 1 says, a light wave traveling through air strikes a flat, smooth surface made of fused quartz. So right away we have two media. Here's air, it comes in at an angle of 25 degrees, so let's draw a normal. And then the light wave comes in at an angle of 25 degrees here. That's theta I. We know that the index of refraction of air is 1, and it hits fused quartz. Now, if that's theta I, and we're hitting fused quartz, and relatively speaking, that means we're going from a faster moving medium to a slower. Not slow, but slower than air. It just means relatively speaking. If you're going to a slower moving medium, remember, it always bends towards the normal. So this angle here is going to be something pretty small. It's going to be less than 25 degrees for sure, and that's what we're trying to figure out. And we know that the index of refraction of fused quartz from our table is 1.458. Go right ahead to use Snell's law. Ni sine theta I equal Nr sine theta r. We're solving for theta r here, which means we divide by Nr to start. Let's get rid of this Nr over here then. Go ahead and think about how do we get theta r by itself. Well, currently it's the argument of the sine function. So we have to take what's called the inverse sine function of both sides, or sine -1 of both sides. So you literally do like this, sine -1 of the entire thing. Those two things equal. Now, here's the thing. Sine inverse and sine, mathematically this is not correct, but they kind of cancel each other out. And what it really means is when you take the inverse of a function, you get back to the independent variable, which in this case happens to be theta r. So this yields just theta r over here, and this theta r is equal to this entire expression right here. So what you really need to do in your calculator is figure out this value first, and then do the sine inverse of that answer. And to do the sine inverse, you press second sine and make sure your calculator is on degree mode. What you would get for this little argument here that I've circled just now in red, what you get for that number would be 0.2898. So you're really just doing the sine inverse of that number. And make sure that you keep at least 4 decimal spots here, because you're going to get a decimal for your degree, and the answer will be much further off if you don't. And you're going to end up getting 16.9 degrees. So an angle less than 25 degrees, as we stated earlier from the diagram here, it had to be less than this because it's smaller. It's going to a slower moving medium. Example 2 says a light wave travels from air through an unknown medium. If the angle it hits the medium at, with respect to the normal, is 30 degrees, and the angle of refraction is 12 degrees, then determine the material it passes through. So in this problem, we're going to try and determine really what the N value is, NR specifically, of the material. So we can then compare it to our table of values and figure out what material it actually turns out to be. So we can take a look here and realize that we've got two angles here. We've got our angle of incidence first as 30 degrees. And we've got our angle of refraction as 12 degrees. And clearly the 12 is less than 30 because we happen to be again going from air to a slower moving medium. We know the N value of air is 1. We know that the N value of the unknown material is unknown. So let's go ahead and solve. And you could really, if you wanted to, solve for any of these variables first before even writing the equation out. Like here, if you're just solving for NR, you divide by sine theta r. And now we can just erase this last part here, or simply cross this portion out. It's now gone. So this is what we're going to do. We're going to plug in 1 times the sine of 30 all over the sine of 12. And that will give us an answer of 2.4. Well, if we go to our table and look at our materials, we'll see that diamond has an index of refraction of 2.419, the closest one on the table.